Hello everyone, this is the video lecture of section 8.2, first part. Okay, so in section 8.1 we learned the limit of concepts, a limit of sequence, the concept of limit of sequence. Today we talk about series. 8.2 is about series. So, series is additive expression of the terms of given sequence. Like this comes from arithmetic sequence. A(n) equals n. 1, 2, 3, 4. What happens if we keep adding? By the way, we only consider infinite series. Finite series is not important. They all obviously have some number result. Now in this case, if you keep adding, the running total, is it going to converge to some number? Of course not. It keeps getting larger and larger, right? So I from 1 through n diverges. Because as you keep adding, so you have to think about keep adding the terms, then your running total, is it approaching some number or it's just divergent? The next example is, this is divergent series. This series does not have a finite sum. Call it divergent. What about this geometric series? 1/2 to the n. Or 1/2 to the nth power. If you keep adding, what happens? Well, the S1, so the first term is, sum of the first terms is 1/2. Sum of the two terms, the first two terms is 1/2, 3/4. 3 plus 1/8, 6/8, 1/8, 7/8. What is it? 15/16, right? You can write this one as 1 minus 1/2, 1 minus 1/4, 1 minus 1/8, 1 minus 1/16. You see the pattern, right? So if you add up to the nth term, we are certain that this is 1 minus 1/2. Getting larger and larger, but it only approaches 1 from below, right? So in this case, as you add more and more terms, the running total up to that point, that running total is approaching 1, right? In that case, we say that sum of this infinite series is 1. Obviously, when you have a finite sum of infinite series, we call it convergent series. So I just talked about running total is approaching. So the way we determine convergence of series is by observing running total as you add more and more terms. You add 5 terms and look at what the value is. Then add 6 terms, 7 terms, 8 terms, 100 terms. 1,000 terms. As you keep adding more and more, and you watch the value, the result of the sum, right? You are observing how that sum value behaves. That sum, running total, is what we call partial sum sequence. It means this. We call it Sn. A1 plus A2 plus. This is, S1 is A1, S2 is A1 plus A2, S3 equals A1 plus A2 plus A3, An is A1 plus A2 plus all the way to An. So this is called partial sum sequence based on the sequence An, right? So Again, S1 equals A1, S2 equals A1 plus A2, S3 equals A1 plus A2 plus A3, keeps going, right? So, out of the base sequence, when you consider series, you can create another sequence called partial sum sequence. This is what we call running total sequence, right? Running total. This definition, not a quotation mark. This is total. Okay? So, as I said here, the convergence is determined by, the convergence of series is determined by the new sequence, partial sum sequence, convergence of partial sum sequence. The running total is approaching some value. Okay? So, definition. A series series just additive expression. Okay? Forever is set to converge, to lowercase s. If and only if the running total is approaching s. So running total or partial sum sequence approaches that value. Here. Okay? And obviously, a series is said to be divergent. If and only if it is not convergent. Okay? If the series is not convergent, we call it divergent. Alright? So convergence, the question of convergence of series of AN, sigma AN, is just a question of convergence of new sequence, partial sum sequence Sn, right? So we don't need to develop whole new theory about convergence of series. We just apply the theory we know about sequence of the convergence of sequence, because it is in the end it's a convergence of this sequence, partial sum sequence. Okay, now the first example will be obviously geometric series. Geometric series. So let's say A plus AR plus AR squared. Keep going. Okay? So we want to consider convergence of this infinite geometric series. First term is A, common ratio is R, right? In order to get the next term, you have to keep multiplying by R, common ratio R. Or the next term divided by the previous term is always constant R. Okay? So, in order to study the convergence of geometric series, again, we have to consider convergence of partial sum sequence. So we have to find the expression of this. You already done this in what? High school math analysis or pre-calculus in college, right? So I will do it this one quickly. If I multiply R times Sn, we multiply the whole thing by R, right? If I write it, so distribute AR squared, all the way to this one times R will be written over here, and then R times this will give you AR to the end. I just wrote this one is one column to the right, so that when you compare this with Sn, they are written column by column. Now I'm going to subtract the second equation from the first. So left hand side is Sn minus R times Sn. Right hand side, so this top thing minus bottom, A minus A. This one cancel, subtracting. So A minus 0, 0 minus this. So what do you get? 1 minus R times Sn is A times 1 minus R to the n. Okay? So, first case, if R is 1, we cannot solve for Sn. R is 1 means just, this is really uninteresting. You keep adding A plus A plus. Then you're adding is A plus then A, all right? Then obviously, so limit of Sn either 0 if A equals 0 or divergence. Right? If A equals 0 means you have a 0 plus 0 plus 0. This is really, it's not interesting, right? So the whole thing is not really interesting. We don't really consider that kind of genetic series. We don't even consider those ones. It's not useful. Really more useful ones. Really useful one is when R is not 1. Then from here, you can get Sn equals A times 1 minus R to the n over 1 minus R. Okay? Because no longer 0. You can divide both sides by n. So, well, and then in that case, when do you have convergence? You know, here, A. If R is between -1 and 1, or you consider absolute value of R is less than 1, then as n goes to infinity, R to the n. We already learned that, right? Exponential function of n, your base is small, absolute value is small. 1/2 to the n keeps getting closer and closer to 0. -1/3 to the n. Alternating but still getting closer to 0, right? Any number between -1 and 1, not including 1 and -1, 0. If R is less than or equal to -1, -1 against 1, -1, 1, -1. Anyway, or R is greater than 1, then this one is either oscillating with wider and wider, or keep getting larger and larger in this case. So anyway, this will be divergent. So Sn will be, the others are all constant. If this one is divergent, keeps getting bigger or widely swing, divergent, right? In that case, your Sn, as n goes to infinity, approaches A over 1 minus R. Because it gets going to 0. A over 1 minus R. As n goes to infinity. Okay? So we don't consider this one. We don't even consider. So it's divergent, right? Let's consider a is not 0. So don't even consider this. Divergent. So r equals 1 case divergent. Less than equal to -1 divergent. Greater than 1. So everything except for this is divergent. Right? So our conclusion is this one equals a over 1 minus r. If your common ratio is absolute value is less than 1, or diverges otherwise, all right? Which means r is less than equal to -1, or r is greater than equal to 1. Altogether, when absolute value of r is greater than equal to 1. And we are assuming a is not 0. If a is 0, is everything 0 then 0? Yeah, obviously convergence. Not interesting. Okay, so let's do first example out of this geometric series. Now, this is what you have to remember. The sum of the infinite geometric series where your common ratio is absolute value is less than 1 is first term over 1 minus common ratio. Okay, first term. No matter how you write your series, you just find first term and common ratio. Okay? So for example 1, a n equals 1 to infinity. That was the second example in the beginning of this section. Oops, starting from 1 half, right? At the time, what did we find? We were convinced that this must be converted to 1. And let's see. Now, here, your r equals 1 half. So it's convergent. Convergence, right? Between -1 and 1. So, what is first term? First term is 1 half also. So this must be a over 1 minus r. 1 half over 1 half. Yes, as we expected. It will converge to 1. B. You have minus 3 to the nth. Something to the nth, something to the negative nth seems to be some kind of geometry or close to it. Now, we want to write something like this, or at least r to the nth power. So let's rewrite it to figure out what this one is. This is -3 to the nth, 5 squared, 5 to the negative n, right? Which in turn can be written as -3 to the nth, 25. This is 1 over 5 to the nth. And then I can combine this one. I just want to make it some base to the nth power, exponential function. That would be 25 times -3 over 5 to the nth power. So that means each term you keep multiplying by -3 over 5. So your common ratio of your geometric series is the base of this exponential function, something to the end. Now, 25 is not your first term. Here, this was a was first term because I wrote it a times r to the n minus. But you don't have to write this way. You can do that. Just plug in the first index value. N equals 1, r to the 0. That's why it is a. What is a? The first term. Plug plug it in 1. You get 25 times negative 3 over 5. N equals 1, right? 5 cancel 5 times 3, negative 15 is your first. So, and obviously, in that case, this one satisfies a convergence condition. So it is convergent geometric series with first term minus 15, 1 minus common ratio r, right? So this is minus 15 over 8 over 5, 5 over, dividing by this one, 7, 5 over 8. Okay? So the key was here to rewrite this one as, some number, constant times something to the nth time, to figure out what the common ratio is. Okay? Next, C. N runs from 1 to infinity, 2 to the 3n, 7 to 1 minus n. Okay, we have to write something to the nth power. This is 2 to the third to the nth power, times 7, 7 to the negative nth power. So this is 8 to the nth power, 7. Okay, I'm going to write 7 first. And 8 to the nth, 1 over 7 to the nth, right? 7 to the negative 1 power to the nth power, 1/7 to the nth power. So it's going to be 7 times minus 8 over 7 to the nth power. So what is r here? Common ratio r is the base of the exponential term, exponential form, minus 8 over 7. Is it convergent case? Well, absolute value is 8 over 7. It's greater than or equal to 1. So it is divergent. Okay, divergent. All right. Next example, you're already, familiar with this. These are all actually reviews of this mathematicism or pre-calculus. And write the following as a ratio of integers. So standard form of rational number. A 0.777 rebel bar. B 0.2323 forever. We use this bar notation to represent repetition. Okay? A. Why suddenly we have this out of nowhere in the middle of coverage of infinite convergence series, infinite series, and less infinite geometric series here? It's because I can write this one as like this 0.7. This one can be considered as a sum of this series. Keep adding numbers each time you go down one digit. Right? You can consider this a keep writing this, keep adding these number. You keep adding number 1/10 size of the previous number. That's precisely geometric series, right? You can write this as 7 over 10 times 1/10, right? 7 over 10, 110 squared. 0.0, right? 007. 7 over 10. So this is geometric series. Common ratio equals 7 over 10. So between -1 and 1. So it is convergent. And no, 1/10. Absolute value of r is less than 1. So convergent. So by formula, a over 1 minus r, 7 over 10 over 1 minus 1 over 10. So we multiply top and bottom by 10, 10, 10, 7, 10 minus 1, 7 over 9. Okay? And numbers. If you have 0.5555, whatever, then this is same idea, right? So instead of 7, you're going to have just 5, right? Instead of 7, you're going to have 5. It's going to be 5 over 9. So the most famous one. Here, instead of 7, you're going to have 3. 3 over 9. Alright? That's why it is 1/3. Okay? And then, okay, let's do this. 0.232323. This one also can be written similarly. 0.23 plus 0.0023. So each time you go down by 2 digits, right? So you're adding numbers 1/100th size of the previous number each time. Again, this is geometric series with first term 23 over 100 and common ratio 100. 2 this down means they're 1/100th of the size. Right? Again, your first term is 23 over 100. Your common ratio is 1 over 100. Again, absolute value of common ratio is less than 1, so it is convergent. And by the formula, 23 over 1, a over 1 minus r. To simplify, I'm going to multiply 100, 100 to both sides. So 23 in the numerator, 100 minus 1, 23 over 9. So as you can guess then, remark or note, whatever. If you have a 17 bar, then instead of 2, 3, you're going to have 1, 7, right? 1, 7 over 9. Okay? If you have, 83 bar, then it's going to be 83 over 9. I want to make a short remark before we do the last example of the first part of section 8.2. That is 2 more remarks. So then, what can you guess? Let's say 217 bar. Can you guess? If you look at it, 217 plus 0.000217 plus 0.00000217. Each time you go down by 3 digits, 1,000. So you're going to go through the same thing. It's going to be 217 over 99. Easy. Right? Well, what if you have a 1.76, let's say. In that case, you just write it. So it's just 1 plus 76 over 99. Okay? And then just combine 175. Okay? And final So what is this? Forever. According to this work, it's going to be 9/9 exactly 1. Right? Are you convinced that this is exactly 1? Don't you feel that this is, yeah, very close to 1, but not exactly 1? And how can you say it is 1? Think about it. Some of you already have thought about this one. Was a little bit confused. If it were, you should have 1 exactly. The fact that you have 9 means that it is not 1. It is less than 1. But here I say equal to 1, not approximately same as 1, right? Is it really 1? Don't you feel that this is something a bit strange, right? I like this example because this one stipulates the core concept of limit. Go back to the concept of limit. Let's say limit of 1/2 to the n power, n goes to infinity. What is it? It's getting smaller and smaller and smaller. Yeah, it approaches 0. We said the limit is equal 0, not approximately 0. Now, does it mean that this term, this sequence, ever be exactly 0? No. The limit was the number. These terms will be getting indefinitely closer and closer. So limit value is not the value, it's not necessarily the value you are going to get actually eventually, right? It is the target number you're approaching to, right? Whether you actually attain it or not. Just the target number you're approaching. As long as you're getting closer to indefinitely, closer and closer. So this notation is not one of the values of the terms, but the target number it is approaching. That's why it is exactly equal to 0. We're not talking about this value, actual value. It's just the target number these are approaching. Likewise, this one is defined, this one going from defined as sum of the infinite series. What's the definition of sum of the infinite series? That is a limit of sequence Sn, n digits. So your partial sum sequence has n is 9 n 9s. This sequence is 0.9. So partial sum, we are considering running total or partial sum sequence. Is it converging to somewhere? Of course, it is getting closer and closer to 1 indefinitely. And this is the limit of the partial sum sequence, or sum of the infinite series. The target number, this running total, is approaching. Certainly, running total is approaching 1. This is exactly 1. All right? The confusion came from this. Somehow you believe that you feel that some of the terms in the partial sum running total has to be exactly equal to 1. No. The sum of the infinite series is just target number, your running total, or Sn, approaching. Okay? All right. So let's do final example of the first part of section 8.2. Example 3. Find the value of x for which the following series converges. That is, n equals 1 to infinity 2 minus x should be. Okay? All right. Let's rewrite this one. Okay. This one is, I want to write something to the nth power. 3 times 2 minus x to the nth power. Right? So what kind of series is this? So this is geometric series with the first term, a equals 1. A equals 3 times 2 minus x. Common ratio is 3 times 2 minus x. Right? So, well, this one, it converges if and only if absolute value of r is less than 1. Alright? Or a equals 0. Okay? So what is it? Absolute value of r is 3 times 2 minus x. This one is less than 1. Or a. So we don't need it. Less than 1 includes 0. So this is already included here. So we don't have to worry about it. And this one, you can rewrite it. 3 can be taken out of absolute value of 2 minus x is same as absolute value of x minus 2. Right? Absolute value of 2 minus x is absolute value of negative of x minus 2. Absolute value of negative something is same as absolute value of that thing. Right? So, what do you get? Absolute value of x minus 2 is less than 1/3. That means what? Absolute value of something is less than some positive number means that inside number is between that number or negative of that number. Right? Adding 2, 2, 2. 2 plus this, 7/3. 2 plus minus 1/3, 5/3. So your x has to be between 5/3 to 7/3. Okay? Alright, that's the end of the first part of section 8.2. Thank you, and see you next time.